Now let us consider capacitors connected in series. So what is meant by series arrangement? Let us say the positive plate is connected to one side, the negative plate of the first one is connected to the positive plate of the second one, and negative plate of the second one is connected to the positive plate of the third one, and so on. If the connections are made like this arrangement is what we call series. Let C1, C2, C3, etc. are the capacities of the capacitors used. Cn. In series arrangement, Q remains the same. The charge through first capacitor or second one or third one or nth one, that must remains the same. Q constant. Let V1, V2, V3, etc. are the potentials across first one, second one, third one, fourth one capacitors. Now we know that Q is equal to CV, and the total potential is always equal to sum of the individual potentials. That means if I replace all these things with a single capacitor, say CS, equivalent capacity in series, let V is the potential difference across the two terminals. This is my A, this is B. So this is A, this is B. So in between the points A and B, whatever the capacitors are present, all are replaced with a single capacitor. Say its capacity is CS. This is called equivalent capacity in series arrangement. The total potential difference between A and B, let us say V. We know that V is equal to V1 plus V2 plus V3 plus so on Vn, because potential is a scalar. Now V, what is V value? It is Q divided by CS. Here the charge is Q. V1 Q by C1, V2 Q by C2, and so on Q by Cn. So if I take Q common and cancel on both sides, then the equation becomes 1 by Cs is equal to 1 by C1 plus 1 by C2 plus so on 1 by Cn. When n capacitors are connected in series, the equivalent capacity is given by 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus and so on 1 by Cn. Now suppose if I say n identical capacitors are taken, n identical, that means C1 is equal to C2 is equal to C3 is equal to so on Cn is equal to say C. Therefore 1 by Cs becomes equal to 1 by C plus 1 by C plus so on plus 1 by C, n terms, nothing but n by C, or Cs is equal to C by n. When n identical capacitors are connected in series, the equivalent capacity is given by C by n. Now in series combination, whenever I consider Q is equal to CV, here charge is same. In series charge remains same, therefore V inversely proportional to C. The ratio of the potentials at the conductors is in the inverse ratio of their capacities. V1 is to V2 is to V3 is to so on is equal to 1 by C1 is to 1 by C2 is to 1 by C3 and so on. Inverse ratio of their capacities. Now consider parallel arrangement. So what is this parallel arrangement? Number of capacitors are connected between same 2 points. Capacities C1, C2, Cn. Here this point is A, this point is B. So between these 2 points, potentials remain same. So V is constant. So in parallel arrangement, potential difference across any capacitor remains same, but charges will be different. So let us say this is Q1, this is Q2, Qn. Now if I take all these things are replaced by a single capacitor between A and B, I am taking a single capacitor. This is called equivalent capacitance CD parallel combination CP. V is the potential difference and let us say Q is the charge. So V remains same. The total charge is nothing but sum of the individual charges. Since each capacitor contains some charge, this is Q1, Q2, Qn, the total charge is equivalent charge in the Cp. So we know that Q is equal to Cv, that means Cp into V, this is C1V, C2V plus so on, Cn into V. So if I take V common, C1 plus C2 plus so on plus Cn. So on both sides I can cancel V. Therefore the equivalent capacity in parallel combination C1 plus C2 plus so on plus Cn or sigma C. When n capacitors are connected in parallel, the equivalent capacity is the sum of the individual capacities. Again, if I take identical capacitors, n identical capacitors are connected in parallel, so equivalent now becomes n into C. Capacity increases, n times it becomes. Again, if I take the relation Q is equal to Cv, parallel combination V remains the same. Therefore, the ratio of charges on the capacitors is in the ratio of their capacities. So C1 is to C2 is to C3 is to so on. So parallel combination V remains same and series combination Q remains same. Now suppose four plates are taken. Let us say alternate ones are connected to positive and negative. These two are connected to positive. These two are connected to negative. So what is the equivalent capacity between A and B? So let us consider this point is B, this point is A. I want to find out what is CAB. Assume capacity between any two plates. Suppose if a capacity is formed, let the capacity is C. So in this arrangement, what is the equivalent capacity? So according to this, this plate is connected to positive charge. This is negative. This is positive. This is negative. So normally a capacitor, if I take, this side is positive, this side is negative because it is connected to the ground. So between any two plates, if one side positive, one side negative, then that behaves like a capacitor. So definitely this gap will behave like a capacitor having capacity C. This gap also behaves like capacitor having C because minus and plus, plus and minus another. All positive ends to one end, all negative ends to another end. This arrangement is called parallel arrangement. In parallel combination only, all positive plates are connected to one end. See, all these sides are connected to one A, these sides are connected to B. This kind of arrangement is what we call parallel arrangement. Therefore, the equivalent capacity between A and B becomes 3C. Since I am using 4 plates, I got 3C. That means 4 minus 1 into C. Suppose if n plates are used, n identical plates are used like this. So alternately they are connected. Say positive side, negative side. Then what is the equivalent capacity? Then C dash becomes equal to n minus 1 into C. When 4 plates are used, it is 3C. 4 minus 1. Since n plates are used, the equivalent capacity becomes n minus 1 into C.